All right, y'all. So we're taking the second part of parallelism and scalar product in vectors. We've commonly taken a vector like q, 2 over and 3 down, and said, hey, that's q. Well, what's 3q? Well, it's 3 times as long in the same direction. Duplicate, duplicate. There it is. Right? There's 3q. That's fine. But we're taking a vector, something with two components, direction and magnitude, and multiplying it by a scalar, just a magnitude increaser. We need to be able to multiply two vectors also, like with both direction and magnitude, like multiply vector v by vector w. That's harder to visualize, but one way you might think about it is with forces, right? So if you have a rocket engine pushing on an asteroid in two different directions, perpendicular directions, you'd expect it to move like up path C as it goes, right? And maybe if one force was a little stronger than the other, then you'd expect it to have a different trajectory, right? You'd expect more component in E. Is that going the right way? Yeah. More component in E and less in A, and so you'd expect that. And if you have the components moving in a little more of the same direction, then you'd expect it also to move up D. It all depends on how much of one force's component is in the direction of the other component. Let me give you an idea of what that might mean. So in your text, there's a really long, arduous description of where they get this equation that we're going to use. I think it's really interesting. It takes into account the graphical maneuver from getting from V to W and what that means algebraically, and then also geometrically, trigonometrically, what this length is based on the magnitudes here and the angle between them. It uses the cosine rule and then manipulates it a little bit, right? Changes it into vectors and then cleans it up. I think it's a really interesting derivation, maybe not worth our time because I think there are two easier ways to think about it. So I'm just going to jump to those easier ways. One of these is this. This, I think, makes a little more sense. Let me move my face. So they call the dot product is the product that you get a scalar out of multiplying two vectors. Okay, it multiplies one vector by how much of the other vector is going in the same direction. So it's sort of like if you take an object like a box and you push on, one person pushes on it with this vectored force, right, a certain amount in a certain direction, and the other person pushes on it in this vectored force, right, a different direction, different magnitude. It feels a resultant force, and we're looking just for the magnitude of that. And it really depends on how much of V is in the direction of W, right? Because partially V is in this direction, but partially V is in this direction. And so we're really only taking into account this component of V and all of W, right, to see how much is in the W direction. So one way to think about this is the dot product, the multiplication between these two vectors, is the magnitude of W, that's this piece, and the magnitude of the part of V that's in the same direction, just this piece, right? Another way to say this piece, the part of V that's in the same direction, is this piece, V cosine of theta. Right? If you remember back to trig, V cosine of theta gives you this side, right? If this is V, this length is V cosine of theta. We can go back to some trig if that's a little fussy, but this is one way to think about the dot product, the multiplication of two vectors. You can see that order doesn't really matter if you have the top one is W and how much, here's W, and how much of V is in the same direction. That's this piece, v cosine theta. Or you can multiply by the same thing. You can have v, this piece, and how much of w is in the same direction. So w is, here's this piece. And they'll be the same value. So don't worry about switching those. So let's try one together. We want to find the dot product, the multiplication of vectors a and b here. Here's vector b. Let's do it in a different color. Here's vector b. Here's vector a. They tell you this one's 10 units long, that one's 13, and here's the angle between them, almost 60. So we can use our fancy dot product equation and say, hey, the dot product of vector a and vector b is the magnitude of the two, 10 and 13, which they helpfully gave us, and the cosine of the angle between them, right? Great. And so you multiply them out, you get something like 66. Cool. Another way to do that, we're going to use the same idea, right? Another way to do that is, depending on what you're given. Here we're giving all of the information, but sometimes we're not given the magnitudes, and we're just given the vector itself. Sometimes a faster way to do that is just multiply the parts of each vector that are in the same direction. So you'll multiply these parts are in the same direction. This one's negative though. And these parts are in the same direction. And they're both positive. So another way to think about the dot product is multiply the x components, the y components, and the z components. Right? So here's a way you can think about that. Right, we're going to do the same sort of thing with this to find the scalar, the dot product of a and b. Well, I know that a and b has an x component here. That's this piece. They each have an x component, and they each have a y component. That's this piece, right? And so that's that and that. So we can multiply those two. And that's another way to find the scalar multiple of these vectors, right? Around is 66. Okay, so kind of heavy, but let's try to apply it. We can take that same idea, right? We can take our equation from here that we were messing with before, and often you can find the angle between. They'll say, hey, here's a vector and here's a vector. Find the angle between them. And you can use that with this, right? We just took our dot product and we solved for cosine theta, and so it changes our equation around, right? So not a big deal, because we have two ways to find this numerator, right? One of which is this way, right? Multiply and add the components. So that's a sneaky way to do this. So now we have a method for finding theta. So this is another way to think about it, right? Please don't memorize this formula. This top part is what we just did in the previous one. Multiply and add the x components, the y components, and the z components, and divide by the magnitude of the two vectors, right? So this is horrible. Please don't memorize it, but I hope that you can do this piece using what's here. Let's try it out. Oh, geez. These are algebraic properties of scalar products. It just, the vectors work in the same way as just regular algebra. So you can check those out, but we'll see them as they go. Let's try these. Let's try 29 first and 30. I'd like you to look at just the dot product between these two, and then also try to find the angle between those two. And then this one's a little tricky. Find t such that, given that a and b are perpendicular, think about what the angle between a perpendicular lines should be. Great, try that, go. All right, so if we're trying to dot product these, multiply them, we can just take, one way is just take the components and multiply the x components together and the y components together and the z components together and add them up, right? Ping! So there's our scalar product of the multiplication of these two vectors. Fine. If we're trying to find the angle between them, like you have angle P and Here's angle Q, maybe coming out of the board at you. You want to find that angle between them. We're going to need this piece to solve for theta, right? So if we rearrange our equations, solve for cosine of theta, we have the dot product. It's right here. So we're going to put that in here. There's -4, right? And these are just the magnitudes of P and Q. And you know how to find the magnitudes of P and Q. Just square each component, add them up, take the square root. That's what this is, right? 4, 9, and 1. This is 1, 0, and 4, right? That's what these pieces are. And you end up with -4 over root 70, and that is cosine of theta. So you have to take the inverse cosine of that answer, and you get about 119 degrees. And so that's this angle. Careful your calculators in degrees. Great, fine. With this, if A and B are really perpendicular, right? Here's A, here's B. This is kind of theoretical, right? How much, like, if this was B, sum of B's component is in the same direction as A, right? But B is perpendicular. So how much of B's magnitude is in the same direction as A? Well, none of it, right? So you can think about it this way. Since A and B are perpendicular, when you multiply them, you're going to get 0 as the product, right? Because none of A is in the same direction as B and vice versa. So you know that if you multiply these, you should get 0. That's a property of being perpendicular vectors. So then you can keep going with that and say, well, I know that the product of this times this right here, if you add that to the y values multiplied, that should give you, that should give you 0, and you just solve for t. It's 2/5, right? It's a sneaky trick that the IB likes to pull, but it hopefully shows them insight that you know that they need to be, the vectors need to be at least in the same, somewhat in the same direction, have components in the same direction to have a scalar multiple at the end. Cool? All right. The only fussy bit about this, I'm being picky about this, is that it's okay to say 3 times 2 is the same as 3 times 2 with the x and 3 times 2 with the dot. But this dot product and the cross product are different. Right now we're talking about the dot product. We will get to the cross product later, but for right now, V dot W, big fat dot, right, is the scalar multiple. This gives you a number out. Cross product is a little different, and we'll get to that later. Cool? These are what we'll attack when I see you next. I hope that wasn't too overboard, but you guys are tough. You'll get it. Okay, bye.